All right. So, last time we spoke about, well, I gave an introduction to Lie groups. So these are groups which, like the circle, form a nice smooth space. The circle is the simplest one, pretty much. And then we have the next simplest one that you're most familiar with is SO3, the group of three-dimensional rotations. And in both cases, and in all cases, there is a special point on the group and therefore a special tangent space. That tangent space is the tangent space to a group. And so that tangent space inherits a structure. It's not a group well, it inherits a bunch of structure. Obviously, it's a vector space. So you have addition of vectors in the Lie algebra. But it also has this extra structure which measures the failure of the group to commute. And this is the commutator of matrices, but otherwise known as the Lie bracket of elements of the Lie algebra. And we saw that the Lie algebra of the circle is the imaginary reals. And, or if you wish, you could think of it as a 1-by-1 matrix with imaginary entry. And then the Lie algebra of SO3 is, oh dear, okay. Now this thing is not working. Okay, so, and then SO3 is a three-dimensional space with a group structure, and its tangent space consists of the skew-symmetric 3-by-3 real matrices. And then finally, we looked at the unitary group, which is a generalization of the circle. It's not the unit norm complex numbers, but rather the unit norm complex matrices. And the Lie algebra of this group consists of the skew-adjoint transformations. So U, right. And then we spoke about the fact that there is an evolution map where you can begin at the identity of a group and choose a tangent vector, an element of the Lie algebra, and then exponentiate for a certain amount of time that matrix, and that will produce a path on the group which reaches a certain point on the group, certain group element. And the typical example of that is the relationship between the real line, which is the tangent space to the identity of the circle, and the circle itself. So the Lie algebra is being wrapped around the group in this way. Okay, and right. Okay, so now here, this is the starting point for today. So I want to look at this picture. So I explained that if you look at all n by n matrices, right, then inside this space, inside the space of n by n matrices, we have the unitary n by n matrices, and then we have the tangent space to the unitary. And this tangent space is what I've drawn here in orange. It's the skew-adjoint matrices. And the skew-adjoint and the self-adjoint are complementary real subspaces of the Lie algebra, and they are related by multiplication by I. I mean, this is somewhat of a convention. If you take a skew-adjoint matrix and multiply by I, it'll become self-adjoint. Just because I complex conjugate is minus I, then multiplication by I can switch between. And it's by convention that we usually multiply by minus I to get back, just so that multiplication by I and my minus I gives 1. So so this shows up. I'm just going to say it in words. It's an important and annoying kind of fact, but when you when you take a quantum system and you want to evolve it in time, right? The evolution in time is given by a solution to the Schrödinger equation. And the Schrödinger equation says that the state is evolving in time by a certain linear operator that's acting on it. And that linear operator it's e to the minus I h bar times the Hamiltonian, or minus I over h bar times t times the Hamiltonian, psi of 0. So the solution to the Schrödinger equation, remember the Schrödinger equation says psi dot is minus I h, minus I over h bar h psi. Okay, so the h bar is not so important. We can set it equal to 1. So let me get rid of it for now. But the important thing is that there is a minus I there, and that surprisingly is very important because it takes the self-adjoint operator H, which is the observable of energy, okay, and it converts it into a skew adjoint, okay, and because this together with this forms something skew adjoint, this means that this exponentiation is a unitary matrix. And because it's unitary, this operator, that means that it will preserve the inner product. So if you have a state, two states which have a certain Hermitian inner product, then upon unitary evolution, that inner product will not change. Okay, so in other words, the Schrödinger equation the Schrödinger flow will preserve the structure that you have in the underlying quantum mechanics. So let me just begin by just writing that down. So since an observable, and in particular this observable, the Hamiltonian, is self-adjoint, minus I h bar is skew adjoint, and therefore is in the Lie algebra of the unitary group. And as a result, the solution of the differential equation, of the Schrödinger equation, and let me take it to be time independent. Let me assume that H is time independent, just to make everything simpler. So we get a unitary evolution. Okay, so what I'm doing here is I'm just making a link between what we've been learning about Lie algebras and Lie groups and the fundamental laws of quantum mechanics, right? The fact that the Hamiltonian itself adjoint is very much related to the fact that we want time evolution to preserve the structure of the vector space and the inner product. Okay, and yeah, I hope that makes sense. Any questions about this so far? Okay. If there's nothing else, then let's go back to the tensor product. Okay. The reason I'm doing this tensor product stuff is because I want to be absolutely clear on how to combine quantum systems. It's really part of the really part of the axioms of quantum mechanics. So it's only if we know how to combine systems that we can really, you know, proceed with doing things like quantum computation and so on. Okay, so let V1 and V2 be sorry, for some reason this thing is not registering my pen. That's okay. So tensor product. So let's V1 and V2 be complex vector spaces. Okay, then we have various ways of combining them. The most typical way might be the direct sum, which is something that has a sum of dimensions, and it's very easy to understand what it is because it's really the underlying set is nothing but the Cartesian product. Sorry, 1 second. I have to fix this. It's not accepting my input. Okay, it seems to be okay, but whenever I turn on Zoom, Zoom is not letting. Okay, I'll try to keep it going, but it's strange. This hasn't happened before. Okay, so this one is particularly easy to understand because it's really a Cartesian product, and so it makes sense to just think of the two vector spaces being you know, a vector. You could think of a vector in V1 plus V2 as an ordered pair, V1 comma V2. So in terms of a data structure, it's just a pair object or a tuple, right? You just have whatever information is needed to describe V1, and then you just append the information describing V2. So there isn't any, you know, and then, so one construction, which is the sum construction, it takes V1 and V2 and outputs V1 direct sum V2. And if we have, let's say, linear maps S and T from V1 to U1 and from V2 to U2, okay, then we have a notion of taking the sum of the maps. So the sum of the maps is very simple. The sum of the maps acting on an ordered pair is just SV1 TV2. Okay, so this is S and T are acting on V1 and V2 separately. All right. So the second construct, the important construction is the tensor product. So the sum is analogous to a sum, and the tensor product is analogous to a product. You might even say that the direct sum of vector spaces is a so-called categorification of the sum of numbers. And you might say that the tensor product is a categorification of the product of numbers, because it's the same operation on dimension, but it lifts that operation to the actual vector spaces. So the tensor product takes V1 and V2 and outputs V1 tensor V2. And this space, this is the vector space consisting of bilinear expressions. Or rather, I'll say it's the vector space spanned by bilinear expressions in of the form, let's say, U tensor V, where U is in V1 and V is in V2. So bilinear expression, what do I mean? It just means that in this type of symbol, so this is the notation. We take a vector from V1 and a vector from V2, and we put them together, but instead of putting a comma, we put a tensor product symbol. And this expression is bilinear in the sense that when we have a linear expression, a linear combination of vectors in either of the arguments, that it comes out in this way. And similarly for the second argument. Okay, so what does this mean? So it's often said that when you tensor two vectors together, V1 and V2, or U and V, and you tensor them to produce U tensor V, it's often said that that is not an operation at all, right? It's there's no computation involved. It's just putting U and V together on the page. But the important thing to know is that that operation is assumed to be linear in each argument. And so what that means is that the bilinearity, it means that there will be imposing bilinearity means that there will be fewer elements of this vector space than you would think, right? Because, for example, if you look at this quantity, this vector and this vector are different from this pair and from this pair, and yet they're all related by some linear expression, some linear combination inside the tensor product vector space. So let me just formalize that intuition and say the following: so that if we have, let's say, EI and FJ, if these are bases for V1 and V2, then what's clear is that any kind of expression of this type, you could express you could express u in terms of the basis, so it would be a combination of the ei's, and you could express v in terms of its basis, so it would be a combination of fi's. So this u tensor v would look like a sum of u I ei and v would look like a sum of vj fj. And because this operation is bilinear, we can just take all the numerical factors out, and what we'll get is ui vj sum over I and j of ei tensor fj. Okay? And so we see here that that the tensor product is spanned by such expressions ei tensor fj, and indeed they form a basis. So then this ei tensor fj, there's now going to be m times n of them. Okay, form a basis for v1 tensor v2. Okay, and as a result, of that, the dimension of v1 tensor v2 is the product. So for example, if I take, C2, tensor C2, tensor C2, this will have dimension 8. So this is isomorphic to C to the 8. And so sometimes you'll see notation somewhat like this. So just let me just look at this example. Suppose that C2 is the span of 0 and 1. These are the two states of the switch. This is notation for 0 and 1 eigenvectors for H in the switch, in the qubit that we studied before. Okay, so any state of the system is going to be a linear combination of off and on. And so this means that C2 tensored with itself 3 times has basis. It's possible that all 3 switches could be off. It's possible that the first 2 switches are off and the third is on, and so on, all the way down to the possibility that all switches are on, right? And so there will be 8 possibilities, and all of these, and by the way, maybe it's useful to mention that this would normally be called, so just to shorten notation, they'll sometimes call this, 0, 0, 0, or 0, 0, 1, and they might list the eigenvalues in this way. Okay, now, so far I've only discussed combining the vector spaces and tensoring them in this way. Let me, before I ask for questions, I'll do questions after the quiz. For now, let me just excuse me, state the next important way of combining. So this is combining one quantum system with another right yields so first of all, the vector space is V tensor U. And then the inner product on V tensor U must be a combination of the two inner products. And what does this mean? So I need to explain, it's not so difficult to see what it is, but if you have V1 U2, U1 V2 tensor U2, then you can certainly take the Hermitian inner product between the V's using the V metric, using the V inner product, and then just multiply the resulting complex numbers. And then we extend this prescription by linearity or anti-linearity. So in other words, if you're a general element in the tensor product will be a sum of such expressions, and so you would like to use linearity to extend what I've given here to a general element. So for example, the inner product of, let's say, 1, 0, 1 and 1, 1, 1, okay, which would normally just be written as 1, 0, 1, 1, 1, 1. It's just a more elegant notation. Would be the inner product on each factor multiplied together. So the inner product between, up, on, and on would be, let's say that 0 and 1 are an orthonormal basis for the vector space. So then this would just be 1 multiplied by 0 multiplied by 1, and so therefore would be 0. Okay, so with this inner product, you can see that so this would imply that the tensor product of orthonormal bases is an orthonormal basis. If we use this this definition of the tensor product of inner products. Okay, I'll continue this after the break. So there's going to be a quiz starting at 2:59 on your Quercus. It's just a few true or false questions, and we'll resume at 3:15. Okay.
So we should start the quiz now.
If you can, yeah, start now.
Okay.
Just a quick heads up, the undergrad, or at least I, seem to have only one question. Whereas some grad students were saying that they have 7. You're muted.
Have you started the quiz yet?
Yes,
How many questions do you see?
1.
Have any of the grad students been able to open it?
I'm doing it right now and I have 7 questions. And I'm a grad student.
Okay, because maybe it's because I opened it last time that I can't open it now.
Yeah, same.
It says my quiz has been muted.
Same.
Should we just make a new quiz, or would that be not helpful?
Well, does your one question happen to have 7 sub-questions?
No, it's just one question about
Okay, that's enough. Thanks. That's strange. Okay, let me try to. Okay, I think you should have all the questions now, and I've extended the time, so please go ahead and relax.
And then for Kat and I, we opened the previous quiz, and now we can't access this one. We're with the graduate side.
I answered the one question, and I can't open the quiz.
Yeah, same here.
I think
This is going to
everyone,
be fun.
yeah.
I'll deal with it. Just maintain radio silence.
Can I ask a question about one of the questions?
What's your question?
Question 5, you say any self-adjoint operator. Do you really mean exclude like just self-adjoint, not linear?
Sorry, I don't know what a self-adjoint nonlinear operator is. I apologize.
Okay, fair.
Besides Gina, who else was not able to get the
Me,
entire?
Me, Kata.
Oh, okay. 1 second.
Also me.
I think I see it now, so it's working.
There's also several undergrads in that position, as can be seen in the chat.
So mine's working now, but it says I only have 3 minutes.
Yeah, same for me.
How many minutes do you need? I'll try to give people more time. How about this? This quiz is I destroy this quiz. This quiz is now destroyed. We continue later. Yeah. Quiz does not count. I'll have another quiz. We'll have a pop quiz at a future date. And I'll make sure that it's always about previous material that we covered in class. I see the celebrations. That's funny. Okay, we'll start again at 3:10. Does everyone now have a quiz available to them? 7 questions and so on? Would you mind completing the quiz, please?
Oh, a new one.
There should only be one quiz in everyone's corpus.
Yeah.
Please answer that quiz.
Are we taking the quiz now?
We are.
Okay, there's 2 quizzes,
No,
which are both called quiz 1 and both have 7 questions.
you're
Does-
not refreshed, I think.
I've refreshed.
I had 2 as well. I just picked one and it had 7 questions.
Yeah, there's still 2 questions, 2 quizzes.
Okay, let me try deleting one again. Romain, do you now see a single quiz?
I do. I'll get started on it now.
Well, thank the Lord for that.
But it's due in 5 minutes, but I guess whatever.
May I ask a question about the quiz?
Sure. Someone wanted to ask a question?
Yeah. When in this context, does unpredictable mean non-deterministic?
I hope that you can understand the question. It's asked in plain language. Just go ahead. Okay, everyone. That was extremely painful. I'm sure it was even more painful for you who had to actually do the test. Let's go through it. Everyone done, right? I think it automatically submits probably. So the first question was, the state of a quantum switch is a point on the two-dimensional sphere. Of course, yes, this is what we just did. It's the Riemann sphere, which is the projectivization of the two-dimensional complex vector space. Question number 2, if an observable has two eigenvalues and the quantum state is chosen uniformly at random, each measurement outcome has probability 1/2. This is false because you don't know how big the two eigenspaces are, right? It could be that in your vector space, there's a million dimensions, which are all with eigenvalue 0, but only one dimension which has eigenvalue 1. So the probability of each outcome, 0 or 1, is heavily favored towards the one whose dimension is larger. Right? This is the concept of having multiple eigenvectors for a single eigenvalue. Question number 3, an observable is any self-adjoint operator? Yeah, that's the idea. Yep, true. If H is the Hamiltonian, then the evolution of a state is given by e to the th v0. This is almost true, but of course, this would not be a unitary evolution. You would not, you see, if you think about it, if H is self-adjoint, then it could be like a 1-by-1 real matrix. It could be just the number 3, right? And then this would be e to the 3t. And what does that mean? That means that the state would be expanding exponentially in time, in size. And that would screw around with all the probabilities. So that's not how the state evolves. There needs to be an I in there. So it's more like e to the I, e to the I th, or e to the minus I th, in order to make it self-adjoint. In order to make it skew-adjoint. Question number 5. If H is a Hamiltonian function and F is another observable, and if they Poisson commute, this means that F is a conserved quantity. Yeah, so remember that the Poisson bracket of H and F can be written as taking the Hamiltonian vector field of H and applying it to F. And if that is 0, that means that F is fixed, is constant along the integral curves of H. So that means that as you progress along one of the H level sets, you're also going to be on one of the F level sets. So H and F are both conserved quantities. Question 6. No matter what state the quantum switch is in, when it is measured, the result is unpredictable. This is false because although it is true for most states that it could be in, if it is exactly at the North Pole or if it's exactly at the South Pole, then you know that with 100% probability, the result upon measurement will be up or down. Anything else that will be unpredictable, but those two are predictable. And question 7, if X and P are canonically conjugate coordinates, then the Poisson bracket is 0. So this is supposed to be almost a joke because the Poisson bracket is d by dp of the first multiplied by d by dx of the second. So there's no way that p and x can commute, Poisson commute. They're precisely the ones that have Poisson bracket equal to 1. Because if you just it's all of the spatial coordinates, they commute with each other, and all of the p's commute with each other, but the p's and the x's could never commute with each other. Okay, that's all. It's just some basic true or falses. Any questions about that?
Yeah, so when we talk about observables, are we not limiting ourselves to physically meaningful observables? So it doesn't mean any observable, that even complex?
Well, I mean, in quantum mechanics, I mean, actually, even just in classical mechanics, right? you could have a very complicated algebraic function or even non-algebraic function of the position and momenta. And you could say, well, is that an observable? I mean, maybe you won't directly observe it, but you might make you might make an observation of something about the state which tells you the value of that function. So it's true that not all functions on phase space are easily or directly observable, or maybe you might say have a physical kind of direct physical interpretation. But in both theories, anything is allowed as an observable. Any function of phase space which has real values is a potential observable. So the way you should think of it is that if you have particular observables that you are really interested in, then that just means that you're making a selection of a certain set of functions, and you're focusing your attention on that, and you're solving for their behavior with respect to time. And the same thing goes for quantum mechanics. Any self-adjoint operator is an observable, and which ones are physical or whatever, that really is just the choice of a subset of these self-adjoint things. Okay, so getting back to tensor product. So far what we have is U tensor V. We have the inner product. And then I just want to make some comments about evolution, or about the symmetries of this big inner product. So this inner product, it has a group of symmetries. This inner product is nothing mysterious. You could just think of it as some huge C to the n, and it has the x bar transpose y inner product that you learned about. And so this will determine a group of symmetries known as the unitary group. I'll call it the unitary group of U tensor V. Okay, and or just to emphasize it, what I'll do is I'll assume that U has dimension m, just like I did before, and V dimension n. This unitary group will be a U m times n. So it will be a very large unitary group. Complex matrices on C to the m times n. Whereas these two, they have much smaller symmetry groups, which are the unitary group UM and the unitary group UN. Okay, so think that the two individual systems, they each have a certain unitary group where their evolution operator, sometimes it's called the propagator, the thing which evolves the state in time, is a unitary matrix. But we have two small unitary groups combining to get a huge unitary group, right? This is a function of the fact that there's a lot more room inside the tensor product than there is in the original constituent vector spaces. Okay, and let me just say that there is a natural inclusion. So if you have, let's say, U inside UM and V, sorry, let me call this U inside UM and let's say U prime inside UN. And if we take little u tensor V inside U tensor V, then I can let I can let these unitary operators each act on their pet vectors. So I can yeah, and that's how I'll define the tensor product of these unitary operators. So I'll define the tensor product to be such that the way it acts on U tensor V is that the first acts on U and the second acts on V. Okay. Of course, if U is inside UM is given, we can promote it to a unitary. Oh, I should have just said that. This should be extended to U tensor V via linearity. And it defines a matrix in UMN. So let me just postpone this for a second. So what this does, what I've just written up here, is that it gives us an inclusion of UM cross UN inside UMN. So a unitary matrix for each piece, for each subsystem, can be combined together to get a unitary matrix of the full system. Okay, and I'm going to talk a little bit more about this, but this is a key idea. Okay, now on the other hand, so in particular, if U is given as a symmetry of the first system, but no other symmetry of the second system is provided, it can be lifted. It can be promoted to a symmetry of U tensor V via U tensor 1. The identity matrix is always available on the second factor. And and I can just act on the first factor. Okay, so this is physically, this corresponds with operating on one of the two systems, not on the other. So if you apply a symmetry to the first system, that symmetry is automatically promoted to a symmetry of the tensor product, just exactly in this way, U tensor 1. That just means you do nothing to the second factor, you do the transformation that you wanted to the first factor. So this operation is called the Kronecker product, and I'm just going to make it a little more explicit in a second. Okay, so the Kronecker product looks like this. So this is just the tensor product on linear maps. And the way it looks like is very simple. It's something that should be taught in 240 or whatever, some linear algebra class. So So I'm thinking now of the qubit. I'm thinking of operators acting on the qubit. I have a symmetry or just an endomorphism, some 2x2 matrix that's acting on the qubit, two-dimensional space, and I have two of them. And I'm tensoring them together so that they now will act on c to the fourth. And so this should give me a 4x4 matrix. And the way that it works, I can write it in terms of the basis, let's say 0, 0, 0, 1, 1, 0, 1, 1. And so that means that from the point of view of the left-hand side, I only see the basis. Yeah, so hopefully this will be clear that it should look exactly like this. So I take the scalars in the first matrix and multiply them by the second matrix, and I produce blocks like this, which give the 4x4 matrix. Okay, and yeah, so you can see, for example, what it does to 0, 0 is that it sends it to AE plus AF plus BE, plus BF. And so this is exactly how the tensor product works from a computational point of view. Okay, now here's the key thing. So any questions about this Kronecker product before I continue? It's not important here that these are unitary matrices. It could be anything. Any linear transformation, just as vector spaces can be tensored, so too can maps of vector spaces be tensored together. And I'm just writing it out explicitly. So even if you had, even if you had a K by L matrix, right, and a P by Q matrix, those can be tensored together. And what you would do is you would just, you would just take, create blocks using the second matrix, whatever the shape of this matrix is. You can place it in blocks, and the shape of those of that layout should be exactly what is dictated by this matrix. So if we had a K by L matrix, so in general, if we have a K by L matrix and we have an M by N matrix, then the Kronecker product will go from Km by Ln matrices. Yeah, exactly. And it'll be a block matrix as above. And it's a block matrix assuming the basis is ordered as above. Of course, I'm assuming that you've ordered the basis for the first vector space, and you've ordered it for the second, and then when you tensor them together, you use something like an alphabetical order that will just like this 0 0 0 1 1 0 1 1. That's in lexicographic order, and then it's going to look like a block matrix, just as I've written here. Okay, so this is important because this is exactly how we go from small systems to large systems. If you have like a crystal that's made up of many sites, then you need to take the Hilbert space or the vector space for each site and tensor them all together. And then whatever the observables are, you need to tensor them together. But we're not quite done yet. Let me explain one key fact. So the key the key result to keep in mind, if I can get my pen to agree to write it. If we suppose that x and x prime are observables, meaning that x is self-adjoint and x prime is self-adjoint, then we obtain unitary symmetries of, let's say, u and v respectively. Let's say these are observables on u and v. So the unitary symmetries that we get from these observables would be e to the I, we could even, yeah, we could say e to the I tx, which goes from u to u, and e to the I t x prime. I could put a minus just to be, let me not put a minus for now, but it doesn't matter. It's both statements are true. So we get two unitary transformations, one of the first vector space and the other for the second. And the way this acts, so the tensor product of this, the tensor or Kronecker product, would be e to the I t x tensored by e to the I t x prime. And if we differentiate this, so this would be a big unitary matrix which depends on time. So this would be the evolution of the joint system. Well, let me not say that it's an evolution yet. This is the combined symmetry or actually a better way of saying it is that this is a simultaneous action of both symmetries on both systems. Okay, and if we differentiate this, what do we find? So we get d by dt at t equals 0 of this e to the I t x tensored e to the I t x prime. This will be, you see, then we're getting a Leibniz rule, because we have two operators acting at the same time, and they each of them has a derivative, and so what we'll get is I times x tensor 1 plus 1, and this is a 1 on v, this is a 1 on u, tensored by x prime. Okay, so you see that the corresponding observable is exactly what occurs here. It's exactly x tensor 1 plus 1 tensor x prime. Okay, so this is not too complicated, but it can be a bit confusing. So remember that you have it all starts with the idea that we have this inner product. The inner product has symmetries. The symmetries is the unitary group. When we combine systems, right, we take a tensor product of the vector spaces, and the unitary action, the unitary group acts on both systems separately. and we get this this combined symmetry where both are acting simultaneously, okay, on both systems. If we differentiate that, right, we have to differentiate each in turn, and we get a sum of observables. So you see here that so that the this tells us that the way observables combine is not by tensoring them with each other. You don't combine the x observable and the x prime observable by tensoring them. You have to take their sum after you've lifted them to the tensor product via this law. So x tensor 1 plus 1 tensor x. So this, by the way, is the lift, or the this is the I said it was promoted from an observable on U to an observable on U tensor V that just doesn't do anything on V. So this is a lift of x to U tensor V. And this is an observable, which is the lift of x prime to U tensor V. And this is just a sum of two, previously defined observables. So this means that when we're trying to combine the quantum systems, if I have U, and H, V, and HV, right? What I'm going to get as the combined, this is the joint system, okay, it can be expressed in the following way. We take the tensor product of U and V, we take the combination of the two bilinear forms, and then we take HU tensor 1 plus 1 tensor HV. Okay, so I just wanted to give the correct explanation for why observables combine in this particular way. And I just want to point out that on this combined system now, okay, the cool thing about this is that the old observables are still available. So HU, so note that HU tensor 1, the Hamiltonian of the old system, this and HV tensor 1, these are certainly other observables. And this corresponds physically to measuring only one of the two switches or systems or particles, whatever you want to call them. Okay, so this is when we're talking about entangled systems. So yeah, let me now make use of this. So with this, actually, we actually come to the end of all of the axioms of quantum mechanics. So now you know what the laws are, what the evolution in time is, and how to combine systems. Let me do an example, and then I'll open it up to questions. Just a very brief example. So let's do a measurement of a combined system. Suppose that we take this system, C2, the switch, with our favorite self-adjoint operator, which measures whether the switch is on or off. So then we're going to take two switches, and the observable which governs, well, yeah, the combined observable will be H tensor 1 plus 1 tensor H. And if we look at what that looks like, so this first one, H tensor 1, this looks exactly like this. And this one looks like this. And so if I take their sum, what I get is 0, 1. Oh, I'm sorry. I wrote this one wrong. See here, this is incorrect. So this should be 1 times the other matrix, which is 1, 1. Whereas this is 1 times this. Okay, so if I sum this together, what I'll get is 0 in the top left, and then I'm going to get this 1. Then I'm going to get another 1, and I'm going to get 1 plus 1 here, which is 2. Okay, so if I look at this combined energy or combined observable, you see that it has 3 eigenvalues, and this is precisely the the configuration of being, if they're both off, that this will have eigenvalue 0. If one of them is off and the other is on, that's a degenerate state of energy 1, eigenvalue 1. And then we also have the possibility that they're both on, in which case the amount of light is 2 light bulbs. So we have the 3 subspaces. So this is a 2-dimensional subspace. This is a 1-dimensional subspace. This is a 1-dimensional subspace. And the sum is a 4-dimensional tensor product. Okay, and so so for example, if I have a state which is a sum of both on and both off, and we measure only the first subsystem, okay, this will give us this means that we are using the H tensor 1 observable. Okay, and this will project to the eigenspace of this H tensor 1 operator. Now look at H tensor 1. H tensor 1 is right here. It's basically 0, 0, 1, 1 down the diagonal. So the eigenspaces of H1, so the 0 eigenspace will be the span, oops, sorry, I should write span of 0, 0, and 0, 1. It's a 2-dimensional subspace of the tensor product. And the one eigenspace is the span of 1, 0, and 1, 1. Okay, so once we make that measurement, the state will be projected onto its component in either one of these two subspaces, right? And so for example, if we measure 0, that means that the resulting state will lie here inside the 0 eigenspace, right? And so how do we figure out what state we get? We need to take the orthogonal projection of your initial state, this entangled state. We're going to take the projection of that onto this 0 eigenspace, but we can see what that projection is going to give. All of these basis vectors are orthonormal, and so when we project this state onto this eigenspace, we are just going to get 0, 0. This will just give 0, 0. And therefore, this is in the 0 eigenspace of one tensor H. Okay, so this is saying that the correct explanation of the entanglement process, or the entanglement kind of defining property, is that if you have a vector like this, which is a tensor product, it's in the tensor product of two subsystems, and it is not decomposable, so it's a sum of two composite vectors, then we can do the following process. We can measure an observable that is only on the first subsystem. That will project onto one of the eigenvalues, one of the eigenspaces of that operator, H tensor 1. And then once we have done that, we could make the second measurement, which is one tensor H. But we can see here that this has been arranged in such a way that it has no 0, 1 component. If this had a 0, 1 component, then when I do the first measurement and get 0, I would have a linear combination of these two states, and I wouldn't know with certainty what one tensor H would measure. Okay, so so the point is just this, that entangled states have this very interesting behavior that you can do subsystem measurements, and they will be correlated in an unexpected way. So here you see that you'll just get 0 because the first measurement was 0. And similarly in the other direction, if we measured this state and happened to get 1, which of course it could be because it has a component along the 1 eigenspace, then it will be projected to that eigenspace, and I'm just going to get 1, 1. Then the second measurement will be in the 1 eigenspace of the second observable. So if you measure 0 first, you're going to measure 0 second. If you measure 1 first, you'll measure 1 second. So there's a correlation between the two measurements, and that is that is a bit strange, considering that these two electrons, or whatever they are, could be separated by light years in principle. Nevertheless, the measurements that you do will be correlated. Okay, I'll leave it there. The next topic that we need to do is we need to get into group representations. So we're going to start with a little bit of the basics of group representation theory next week. Any questions? I'll stick around for 10 minutes or so.
I have a question.
Yeah.
So going back a little bit to this, how we derive the form of the observables of the composite system.
Yeah.
I just wanted to kind of summarize, and I wanted to know if you think this is a good way of thinking about it.
Yeah, go ahead.
We took some self-adjoint operator, and we multiplied it by I to take it to the skew self-adjoint operators, which is element of the Lie algebra of the unitary group. Yeah. And we exponentiate it to get an element of the unitary group.
Yeah.
And then I'm kind of confused about if there's any significant way to describe this differentiation process in that kind of framework of like going from a, some kind of like adjoint map to this, skew self-adjoint operators, and then you take the exponential map to go to the group, and then you're kind of going back down again to the observables. But is this differentiation have like a similar name like that? It's not like the inverse of the exponential map, because that's a logarithm, and it's not, something that I'm not sure what I would call it.
It's literally the derivative of the exponential map. Yeah, it's.
But is that, sorry, I guess I mean, like, is the derivative
the
then
exponential map? The exponential map, basically the derivative at t equals 0 is the identity map. So it's, sorry, I mean, I'm just trying to give an explanation of why the rule makes, why the rule is the way it is. Of course, the way you combine the systems is just by taking h tensor 1 plus 1 tensor h. But the observation is that if you exponentiate that, if you exponentiate x tensor 1 plus 1 tensor x prime, then you will get the, you see, like, all I'm saying is that I'm doing it in reverse. So if you were to exponentiate this thing, which is a self-adjoint operator, so take this self-adjoint operator and multiply it by I, if you exponentiate this, you will get this. You will see that the symmetry treats each part of the tensor product separately. What I was saying has no more information than just that. It's just saying that because we're in the Lie algebra, the way that the observables combine is by addition. And then the point is that, you see, like, maybe you could think of it this way. This is a useful way of thinking. So we have one matrix here, one matrix here, and one matrix here. Okay, and these are, roughly speaking, in the Lie algebra. Okay, not quite, because you need to multiply by I, but okay, do that. Multiply x by I and x prime by I. We have two elements of the Lie algebra, and the point is that these two, these two elements of the Lie algebra of the big unitary group, they actually commute. Okay, because if I take the commutator of a Kronecker product,
yeah, like I see how they commute. Yeah, they're independently acting on state. So
correct. Yeah, and this is the identity. So because x prime commutes with the identity, and because x commutes with this identity, these two operators will commute. And so when you exponentiate this, you're just going to get the product of the exponential of this with the exponential of this. Okay, so don't this equation might look weird if you compare it with something like e to the I t x plus y is equal to is equal to e to the I t x, e to the I t y. I mean, this is just not true for matrices. Okay, but because if x and y commute, then it will be true, and you will get an independent action of e to the x on and of e to the y. So yeah, I would say that most people find it more intuitive that the symmetries should act this way. That if there's two symmetries, you just act, and if you have a vector that's composite, you just act on both vectors by their own symmetry simultaneously, and that's it. This one is maybe a little bit less obvious that this should be the way that you combine the Hamiltonians, but this explanation, yeah. So yeah, the process to go from Lie algebra to Lie group is exponential map, and the process from going to the Lie group to the Lie algebra, you could call it the logarithm if you wish.
Yeah. So then I think my confusion, not confusion, but what I want to maybe put meaning into is going from the unitary group, like the composite unitary group, to the set of observables with this differentiation. Like, does this differentiation have any significance, or can it be generalized in any way to say, like, oh yeah, if I take some group, like can I do this derivative mentality out of the context of unitary groups and just consider a relationship between, a unitary group, or between a group and some other set of operators with this differentiation framework? Does that make sense?
Okay. I mean, I think I understand the rough question, but let me just. So, the Lie algebra of a Lie group is just the tangent space to the identity. So if you have a path of group elements passing through the identity,
okay, I see.
you can differentiate it. Or if you have a path of group elements, then let's say you wanted to extract something out of that path, you could choose a point and say, at this point, what I'm going to do is left translate the entire path to the identity, so that, let me just draw a picture. I don't know if this might be of interest. So you have the identity element, you have a path. Okay, the tangent space to the tangent vector to this path will be a Lie algebra element. That's the differentiation thing that you're talking about.
Yeah. Okay.
Now, on the other hand, it could be that you have your group with your identity element, and you might have a path like this, and you might have a point T naught, which you're interested in. So then what you could do is you could take this gamma of T naught. This is some group element. And you could take gamma and just left translate by G inverse on the entirety of gamma. And that would bring this path so that it's now like this. This is G inverse gamma. And then you could take the derivative at t equals 0 and get a Lie algebra element. Okay, so that's all.
Okay.
Yeah.
These other paths that don't go through the identity, these other tangent spaces, are those just other algebras? They have any specific?
No, they are tangent spaces of the group, and they can be identified with the tangent space of the identity, like I just said, by left translation or by right translation. So there are two ways of identifying that tangent space with the Lie algebra, but they do not by themselves have any special algebraic structure.
Yeah, okay, cool. That makes sense. Thanks.
You're welcome. Any other questions?
I have one, but it might be kind of dumb.
That's all right. I don't mind dumb questions.
Okay. Is there another notation for the Kronecker product?
Honestly, I mean, I would just use the tensor product to denote it. It's just the tensor product. Whenever you learn a vector space operation, vector spaces over C cross vector spaces over C to vector spaces over C, right? You learn many of these operations. They go to, let's say, U plus V, right? You should also figure out how to deal with maps, right? This is going to be sent to U prime plus V prime. But what about the maps? There should be always a definition of the sum map. Any kind of construction that you learn should be extendable to maps. So for example, another one that you learn is just a vector space being sent to its dual. And if you have a map, right, then this goes to W dual. And then you know that you get a dual map going in the opposite direction. So always, so if you take U tensor V and if you take U and V and map it to U tensor V, then again, the tensor product of linear maps should go to some linear map. Okay, so that's you can't learn about the tensor product without learning about the Kronecker product.
I feel like I have a follow-up, potentially dumber question then.
Yeah, okay, go. It's like a de-evolution. That's fine.
Well, so when you take this tensor product, right?
Yeah.
You get states that can be decomposed and states that can't be decomposed. So those are entangled states, right? And if you're considering operators that combine,
Entangled ones are the ones that sorry, which one is which?
the entangled ones are the ones that can't be written as some state from the first system tensor with some state of the second.
Correct. Yeah, correct.
But then the way we combine operators will always allow them to be separated like that. Like, is there any idea of like an operator that's inherently entangled because of it? Like,
Well, wait. I mean, operator. You're mixing states and operators. So
well, that's what I'm trying to get at. Is like
when you have a joint system, right? It all depends on what the evolution observable is, what the Hamiltonian is. So if you have a Hamiltonian like this, H tensor 1 plus 1 tensor H, okay? Or like this, X tensor 1 plus 1 tensor X, then look at how the system evolves. It evolves via, something which is just a unitary operator on the first and then a unitary operator on the second. So that means that the first is not affected by the second at all. The first system is not affected by the evolution that's happening on the second system. So that's the thing, is that if you wanted to let the systems interact, you would have to add a term like an element of the Lie algebra, which is not of this type.
Yeah, like an operator that would have to act simultaneously on both systems and couldn't act individually.
Yes.
Yeah, okay. But yes. You would see that from the form of the Hamiltonian at the beginning, I guess. There'd be some interaction term. Like,
yes, absolutely. Yes. It's exactly this thing. It would not be of this type, something tensor 1 plus 1 tensor something. You would also have, potentially something which is some, we could even do something like this, epsilon times X tensor X prime. That would be a good interaction term, because it would be, what it would be doing is it would be like measuring whether the two states are either 0 or 1, and it would be multiplying those numbers. So that means that the possible eigenvalues of this X tensor X prime would be like 0 times 0, 0 times 1, 1 times 0, and 1 times 1. So it would be mostly 0, but sometimes 1. So I guess you could, I would interpret your question like this, that if you use a Lie algebra element which is produced from Lie algebra elements on the subsystem in this particular way, then the resulting unitary evolution, right, if you start with a decomposed state, a state which is not entangled, a decomposable state, it will remain decomposable always. And it will never go out into the entangled states. But as soon as you add something else to this, then the evolution will be not the Kronecker product of two unitaries, but a general unitary, something which is not in that Kronecker product. Because you can imagine that in this embedding, these are very small. This could be very large. So only a very small number of unitary matrices is of this form. Okay.
Yeah, okay. Yeah.
And that's I guess that's how you could see this. That as long as your tangent vector remains remains a sum of a tangent vector to this and a tangent vector to this, which does nothing to the, then it'll remain on this very small sublocus inside the general unitaries. So yeah, you could really say that interactions between systems inevitably generate entanglement. And that's what I meant when I said a few classes ago that it's the lack of entanglement which needs to be explained. The fact that that most things are not macroscopically, nothing is really entangled. that requires an explanation.
Right. Yeah. Okay, that makes sense. Yeah. Thanks.
Okay.
All right, have a good weekend.
You too. Anyone else? Okay. Have a good weekend, everyone, and let's start again on Wednesday.
Thank you. Bye-bye.
You're welcome. Bye.
Thank you.
You're welcome. Nice tablas.
Thank you.